Human language is inherently chaotic. It is full of unstructured nuance, context, and organic shifts in meaning. To a computer processor built to execute perfectly structured instructions, our language is completely opaque. Machine learning algorithms do not read words. They process reality through matrix mathematics, which means they require strict numerical inputs to function. Natural language processing, or NLP, is the dedicated engineering subfield of artificial intelligence designed to bridge this gap. Its entire purpose is to translate human semantic meaning into computable numerical formats. Early attempts at this translation relied on rule-based heuristics, where engineers manually coded linguistic patterns. Those systems were brittle and failed to scale. Today, modern NLP abandons that manual approach in favor of low-bias, highly scalable deep learning and transformer models. Modern generative AI is not magic. The ability of a machine to write an essay, translate a document, or hold a conversation is simply the culmination of these foundational NLP transformation tasks operating at scale. We are going to deconstruct the end-to-end NLP pipeline. We will trace the data from raw text through pre-processing and vectorization all the way to the final model architecture. The intelligence of any AI model is entirely constrained by how effectively this pipeline strips away human noise to encode mathematical meaning. We start with raw data input. Consider a highly chaotic, punctuation-heavy sentence filled with conversational grammar. First is tokenization, splitting raw text into discrete linguistic units. Next, standardization converts all text to lowercase and removes punctuation and special characters, which rarely carry semantic weight and only introduce noise. We then apply stop word removal, dropping semantically empty words to instantly reduce dimensionality. To fix structural variations, we apply word normalization, choosing between the brute force approach of stemming and the precision of lemmatization. Stemming is syntax-driven, simply chopping the suffix off so running becomes run. Lemmatization maps the word across a dictionary database to identify its root form, cleanly converting ran to run. We must also handle edge cases, expanding contractions and replacing numerical data, like dates or percentages, with static placeholders prevents the algorithm from treating them as unique outliers. Because sentences have variable lengths, we finalize the pre-processing with padding, adding zeros, or truncation, removing excess tokens. This ensures all sequences fit uniformly into a fixed-size input matrix. This dimensionality reduction process forces the infinite linguistic variations of human speech into a standardized, finite vocabulary the machine can compute. Even after pre-processing, our clean tokens are still strings of text. Algorithms cannot process text. Early methods like bag of words and TF-IDF turn tokens into numbers by cross-referencing words with numerical frequency scores, generating a sparse matrix. They capture frequency perfectly, but destroy sentence sequence and contextual meaning. The solution is word embeddings, seen in Word2Vec and Glove. This maps text in a high-dimensional space, encoding words as mathematical vectors. Here, semantic similarity translates to spatial proximity. The king node is plotted right next to queen. The architecture evolved further with contextual embeddings, powered by models like BERT and GPT. Instead of a static location, a word's vector coordinates dynamically adjust based on the surrounding tokens in the sequence. The word bank splits into completely different mathematical coordinates depending on whether it is surrounded by river vectors or money vectors. By plotting words as dynamic coordinates, we successfully translate human semantic intent into pure geometry. Once vectorized, the pipeline diverges into specific neural network architectures depending on the desired NLP task. The first path is text classification, assigning predefined categories to text documents based on their content. This scatterplot illustrates a support vector machine, drawing linear decision boundaries straight through vector clusters. Conversely, deep learning processes this differently. Recurrent neural networks read sequential data to capture long-range dependencies in the text. Transformer-based architectures lead classification tasks, utilizing self-attention mechanisms to model contextual relationships between all words simultaneously. The second architectural path is generative AI and text generation.
The foundational engine here is language modeling.
It understands structural patterns well enough to predict the exact next token based on statistical probabilities. This flowchart illustrates the autoregressive loop, generating text one token at a time. The generated token circles back into the input stream. Natural language understanding components constrain this loop, forcing the model to capture exact semantics, keeping the output accurate. Generating human text is just the continuous autoregressive prediction of the most mathematically probable next coordinate in our vector space. To build modern large-scale pre-trained models, engineers execute this exact pipeline over vast internet-scale datasets and fine-tune them for specific tasks. Because these models are entirely statistical, their generated output cannot be trusted blindly. It requires rigorous mathematical evaluation. This dashboard tracks evaluation metrics. Engineers use blue and rouge scores to measure fluency against human baselines and monitor internal confidence with the perplexity score gauge. Perplexity calculates a model's surprise at its own text. A lower score proves mathematical confidence, yielding higher coherence. Engineers combine these metrics with human-in-the-loop and adversarial evaluation techniques, actively attacking the model to uncover weaknesses, biases, and hallucinations. Natural language processing is a highly engineered, measurable pipeline of tokenization, vectorization, and autoregressive modeling that successfully translates human thought into computable architecture.